We will have a poll.
Yes. Yes, so, okay, that's it? Yeah, okay. All right. Okay, so I was a bit undecided about what to speak about. I like these two topics, and I have different levels of enthusiasm for each of them, and I don't want to spoil which one I have the most. So there's two topics that I could speak about. One of them is about hydrodynamics of driven open systems. So this is about how to do hydrodynamics around non-equilibrium steady states. So these are states that are time independent, but they continuously produce entropy. So there's a way of working around that. That ends being in the realm of what people call active matter, or active matter is a sort of example of an open-driven system that people have studied in physics for a while. I don't have yet very good applications of that in relativistic hydrodynamics for the systems that maybe mostly people are interested in here, but maybe you know of systems that I could fit in there. In the other topic is about magnetohydrodynamics and one-form fluids, so fluids with higher form symmetry. I would show how you formulate that, summarizing what people have done in the past several years in this field, and also look at causality in those theories and numerical implementations of those causal theories. Okay, and if I have some time, which I probably don't, I'll explain a little bit about approximate higher form symmetries and generalized melting. Okay, so now I'm going to ask you to put your hands in the air for which topic you want. Okay, so who would like to hear about topic one? Please put your hand in the air. Who would like to hear topic two?
But someone put it twice. Okay.
You cannot put it twice, otherwise. Okay.
I think we have a winner number two.
Okay. Okay, that's what I expected. So here we go. I don't need to change the keynote. Sorry? No, there was one, but it's in another keynote file. Yeah. Okay, well, thank you very much for the opportunity to speak about this topic that I'm also enthusiastic. Okay. I'm going to speak about a bunch of papers that I have been working since 2018, but I'll also mention many works of people who are also doing this, who are following this line of research, also people who are in this room. So this is my little research group at the University of Amsterdam. It's for postdocs and 3 PhDs that work on hydrodynamics at all scales and complex systems. And this work that I'm going to present is with these two here, Akash Jain and Ruben Lier, who are both exceptional in their own different ways. And also with these two collaborators who work on astrophysics, both Filippo, who's a postdoc at Frankfurt, and Oliver Porth, who's a numerical astrophysicist at the University of Amsterdam. Okay. So what are the motivations to think about this? Well, it seems that the world organizes itself into different phases of matter. You might recognize many of those phases in this plot. So there are plasmas, solids, crystals, quark-gluon plasma, superconductors, ferromagnets, gases. This is a representation of a spin ice material, a material with emergent magnetic monopoles. A superfluid, this is an active liquid crystal. This is an active nematic. This is what's called a metamaterial, an active solid. This you'll never think what it is. You'll never know, never guess. That's my representation of a black hole in higher dimensions. This here is a deep brain in string theory. That thing you might not know unless you lived in the Netherlands. That's the Randstad. That's a segregation map in the Netherlands, segregation in terms of inequality. And this is an active solid as well. So these are all phases of matter that I think can be described using hydrodynamics. And this is just a little bit of the flavor of the phases that are there. People, oh, sorry, I forgot that point there. That's the vacuum, which might also be one of those phases. And people here are typically interested in this, okay? But as a true hydrodynamicist, I like to go over the 60 orders of magnitude possible. And if I would like, instead of writing a hydrodynamic theory for each of these phases independently, if there is a methodology by which I could address all of these in one go, I would be very happy, okay? And that's precisely what higher form symmetries do. All these systems that you see here surrounded by a circle, they have a higher form symmetry of some kind, either spontaneously broken or weakly broken. So an approximate higher form symmetry, okay? So that's a conceptual motivation for this. There are also practical motivations for this, and maybe I'll convince you of that practicality at the very end, okay? Oh, the point again. So just for you to know what a higher form symmetry is, this is just a small, simple cartoon. This is a conventional symmetry. That's a U1 symmetry, has a conserved U1 current. I can integrate that current over a box, and I count the electric charge or the mass in the system. A higher form symmetry, this is what's called a U1 one-form symmetry, is characterized by the conservation of a two-form current that is antisymmetric in these two indices. And it counts the number of field lines that cross a plane, okay? So this would be, for instance, you count the number of magnetic field lines that cross a plane, and that tells you, that magnetic field lines are conserved, okay? You can generalize this to any rank here, and then you get conservation of sheets or branes or any higher dimensional object that you would like, okay? An approximate symmetry is something that you weakly break on the right-hand side. You add some kind of a source term that comes from some controlled way of breaking the symmetry. That small L parameter there is just to keep track of the smallness of that breaking, because I want the right-hand side to be as small as the left-hand side, which is a gradient term. So that L, small l, has to be small. And if you have this sort of thing, now your charge is no longer conserved. Particles could split into two or merge into one. There are several applications of that, especially in systems in which the number density is not conserved. And you can do the same for a higher form symmetry in which the right-hand side is mildly broken. And then what happens is that field lines can join or disjoin, and the points where they join or disjoin are called topological defects, okay? And the interesting thing about the higher form symmetry that is approximately broken is that as a consequence, you have an emergent topological symmetry, because if you have a higher form symmetry, which is with a current that is antisymmetric in these two indices, you can act with another derivative, and that's automatically zero. So that means that the right-hand side is conserved, okay? And what that means is that if you put a box that encloses all the topological defects, you count the number of topological defects in your system, okay? So that's what a higher form symmetry is. Now, I'm mostly going to speak about the fact in the case in which I only have a one-form symmetry, so a two-form current, and it's totally conserved, okay? And that can describe the hydrodynamics of MH or magnetohydrodynamics, okay? Now, in general, there's, many symmetry breaking patterns for what you can choose for these things. There's many words for that, spontaneously broken, explicitly broken, approximate, pseudo-spontaneous, anomalous, temporal, spontaneous symmetry breaking. You will never know what that is unless you're my biggest fan. And then there's different types of symmetries that you can break, and all these things will give rise to all those phases that I mentioned, okay? Some examples here: gases, translation invariant; solid, spontaneously broken spatial translations; superfluids, U1, spontaneously broken. The plasma, I'm going to argue, is a temporal spontaneous symmetry breaking pattern. Spin ice is a pseudo-spontaneous U1 one form. A superconductor is a rather complicated thing. In this language, a D brane is a spontaneous symmetry breaking of a higher group. Okay. All right. So to be more concrete, I'm going to focus on one-form symmetries in my hydrodynamics. And the motivations here is, how do I consistently formulate this with approximate higher form symmetries? How do I do hydrodynamics with that symmetry? How do I describe the equilibrium states of theories with these higher form symmetries? How do I write a partition function, etc. Can stability be dealt in the same way? Are there stability, causality issues associated with this? How do I fix them? And what phase transitions are possible between all these sort of realm of symmetries that you saw? Okay. So this is my outline. I'm going to look at the foundations of hydrodynamics very pedagogically, I hope. Then I'm going to look at causality and stability, then a numerical implementation of that, and then, if I have any time, on approximate higher form symmetries. Okay. So, how do we do hydrodynamics? Let's consider a neutral fluid. I consider that this neutral fluid lives in some space, some general relativity space that is characterized by G mu nu, in many cases just a Minkowski space. Okay. I have conserved energy momentum, and I can write down the most simple isotropic fluid you can think of that depends on the temperature, the fluid velocity, energy density, and the pressure. Okay. Now, hydrodynamics is also characterized by a conserved entropy, or sorry, a semi-positive definite entropy current that has to satisfy that equation. And I can look at or ask the question, what are the equilibrium states in that theory that imposes some conditions on the sources that that theory couples to. So here, if you'd only have a metric in equilibrium, this condition must hold. There must be a Killing vector field such that that equation holds. And then the fluid fields in equilibrium are determined exactly just by the existence of that Killing vector. I can write the fluid velocity as being the normalized Killing vector field and the temperature as a global temperature, and then in terms of that modulus of the Killing vector field. Once I have that, I can write a free energy or a partition function that just depends on the temperature and is purely geometric, okay? I can vary that free energy and I get the stress tensor that I wrote down at ideal order, all right? We all know how to go out of equilibrium. I need to add corrections to that stress tensor. Now we have to deal with the fact that temperature and fluid velocity are not uniquely defined out of equilibrium. It allows for field redefinitions, as it's called. You can shift them by gradient terms. You can fix a frame. The most common one is the Landau frame. In that frame, the second law fixes that the stress tensor at first order is only given in terms of shear and bulk viscosity, that both have to be positive semi-definite. Yeah? How do I do with a charged fluid? I couple it to a gauge field besides a metric. All right? The equations of motion are slightly different. There is a Lorentz force on the right-hand side of the stress energy conservation. There is a U1 conservation, and again, the entropy current has to be positive semi-definite. You can follow the same procedure. You find that not much changes. Now, your current at first order also includes diffusion or conductivity. Yes, that's the only transport difference that you get in a charged fluid. Now, what happens in superfluids in which the U1 is spontaneously broken? The equations are exactly the same. Nothing happens. That's why it's spontaneously broken. Theory has the same symmetries. But there is a new field in the game, which is the goldstone of that broken symmetry. And that goldstone I represent by the phi field that transforms linearly with a gauge parameter. And because of that, I can define an invariant, so-called superfluid velocity, which is this chi over there, and build, again, an equilibrium stress tensor. that now has this anisotropy because of the superfluid velocity, and it has a superflow in the current, okay? Sorry? Mu? You mean the chemical potential? Yeah, that's the chemical potential that is related to the time component of the superfluid velocity. That's called the Josephson equation, okay? You've seen one of those yesterday in the non-abelian case. So now the thermodynamic quantities are a function of temperature, chemical potential, and that new scalar that captures the spatial components of the superfluid velocity, that chi, okay? You can write the free energy functional in exactly the same way, but now this free energy functional shouldn't really be called a free energy functional, but more like an effective action for the Goldstone field, because the Goldstone enters there through chi, okay? And you can vary that effective action with respect to the Goldstone field, and you find this equation, which is the Josephson equation if you include systematically gradients in it, okay? So this means that equilibrium states for a superfluid are degenerate. There's many configurations of the Goldstone field for which there is an equilibrium solution in a superfluid. This is known, but I want you to remember this because this is what happens in the plasma as well. Yes. No, it's only the spatial part. The time derivatives, they're given in terms of this here. Sorry? You could say that, you know, this is an equilibrium condition that you find if you impose equilibrium conditions, okay? Or if you go out of equilibrium and determine the Josephson equation. In principle, there's four scalars. There's mu, there's the time derivative of chi, and the spatial derivatives of chi. I know that one of these is not independent. I remove it, only consider the spatial part. Yes, yes. Yeah, I was not very precise here. It doesn't matter in the end because in equilibrium they're related. So it's just over determining this, yeah. Yeah. So what is MHD? Well, you have a Josephson equation that you have to perturbatively correct. So in that sense, there's not just conservation laws, there's a Josephson equation that determines the dynamics of the Goldstone field. Yeah. So what is MHD? So this is something that some people here thought about also very much, is that the gauge field is no longer a background field, but it is a dynamical field, okay? So now what I do have is a metric and an external current to which this gauge field couples to. That's the source of the gauge field, all right? So what are the MHD equations? There's a conservation of stress tensor, a Lorentz force, and there is Maxwell's equations that couple to this external current, and it's convenient to, you know, rewrite the current here in terms of the field strength, gradient of the field strength, and whatever contributions come from matter, all right? And there is, of course, the Bianchi identity that you have to satisfy on the field strength, all right? You can decompose your field strength in terms of electric and magnetic fields. These are the general expressions that people typically use, okay? Yes? J matter is anything that comes from the fluid, the charges, you know, the flow, anything. The description of the fluid that I'm considering coupled to electromagnetism. That's the charge part. There will be a charge density, there will be conductivities. You'll see everything that can be and will be. Yeah. F mu is the field strength, the D of A. Sorry? Strength is not field strength of all. The field strength is defined as the exterior derivative of the gauge field. F equals D of A. right? Not yet, no, that's a good point. It will be. Okay, so this is the minimal model of MHD that people take in astrophysics, okay? So you have the electromagnetic contribution to the stress tensor, and you couple it to a fluid, and you can see here that your pressure and energy density don't depend on the field strength itself. It's decoupled, okay? It's not the most general case. I'm just giving you the simple case that people consider in textbooks, okay? Now, you can take such a thing, and now related to the question that I just asked about the current, you know, there is a charge density here, there's a conductivity here, you know. This is the minimal model. You can correct this higher orders, you'll see everything there is to see, okay? If you take this and you put it back into the Maxwell's equations that I wrote in this form, you have an expression like this. Here, the charge density, here, the electric field, okay? Given in terms of other things, all right? Now, in hydrodynamics, we always invoke a derivative expansion, right? Sorry? Yeah, of course, it does. So the second law just means this has to be positive, you know. Don't get hooked up on that for now. Just the argument here is something else, okay? So as you can see here, we typically treat this thing in a gradient expansion. This gradient here is the gradient of a field strength, so it will be, you know, at least a first order quantity on the right-hand side. And the same thing here, okay? So this is a first order quantity. At ideal order, I can sort of forget about it. And the same thing here. This was a gradient of a field strength. As first order, I can forget about it, okay? So what happens now is that, as you can see, the electric field will be given in terms of a gradient here, and also this. And the charge density in terms of. If I now assume that this current is weak, that this current is also gradient suppressed, it means that both the charge and the electric field are gradient suppressed, okay? And that is the assumption of magnetohydrodynamics. Sorry? No, in general. So you just assume that you have Debye screening, that the charges can rearrange themselves in your plasma in such a way that the hydrodynamic length scales, they're close to neutral, okay? This is MHD, as in any textbook that you can find, all right? Typically, what people do in a textbook, though, is that they divide the right-hand side by the conductivity, so they move the conductivity to the right-hand side, and they say, my plasma is conducting as much as it can. So they take the conductivity to infinity, which is similar to say the electric field is derivative suppressed, okay? Oh, sorry, that would just say there's also a gradient term. Okay, so what happens is that the assumptions of MHD is that this is gradient suppressed instead of doing that thing, okay? Just more formally instead of sending the conductivity to infinity, all right? And when you do that, your stress tensor, of course, doesn't depend on the full field strength. It will only depend on the magnetic part, on the B field, and then everything else is just pushed to higher order, okay? Now, as a consequence of this is that in a derivative expansion, both the charge and the electric field will never be independent degrees of freedom. They will always be determined in terms of all the other low energy degrees of freedom. Okay? Now, you can go on and, you know, do it more generally. I showed you the minimal model, but now you can actually consider a pressure that is a function of T, of mu, of B squared. So not assuming that it decouples like in this minimal model here, okay? The stress tensor is given in terms of this, the charge current in terms of that, the S in terms of this, and you can impose the second law and see what happens, all right? You can consider equilibrium states in this theory. You couple your gauge field to an external current, such that, upon variation, you get the correct Maxwell's equations coupled to an external current. You can derive the equilibrium stress from here, etc. Okay. You can correct your free energy functional at higher orders. So these are non-hydrostatic corrections. Okay. I now start adding everything I can add at first order. There's 5 of such terms. Okay. I can go to the non-hydrostatic sector and also think about what happens. And there's a bit of a mess, but these are all the coefficients you can get. You parameterize your stress and your current in this way. You choose the Landau frame. There's all these coefficients, okay? The blue ones I just highlight because it's a kind of our contribution, just to be totally thorough here. And what happens is that in the end, there is 5 hydrostatic coefficients, 19 non-hydrostatic coefficients, and if you impose on-Saga's relation, there's 14 transport coefficients at first order in derivatives. If you impose parity, symmetry, time reversal symmetry, you can reduce it to 7. Okay? The black ones are written in no. So the black ones was the work of Sasso and Pavel here. They're not written in Landau-Lifshitz. Say again? When it gets to kinetic theory, that's my handicap. So I don't know, I don't know of all the different kinetic theory approaches to plasmas. I do also know that many of those kinetic theory approaches to plasmas are in different regimes than the MHD. So they consider strong electric fields. It's not obvious to me if I can compare it right away, but I'm happy to talk about it. Okay. It can be finite, but it's not independent. Okay, so this is the point that I'm going to show you now. No, it's charge neutrality in the same way that the charge is pushed to ideal order. Okay, there's no discussion. That condition just tells you that the chemical potential has to be determined in terms of the other fields. Okay, this is what it does. That's what that condition gives you. No, it doesn't. No, that's why it's determined in terms of the other fields. So, this exercise, this is the most important thing, At the end of this exercise, this is the most important thing. This is, once I have the whole shebang of transport coefficients, I can put it back into the Maxwell's equation and literally determine the chemical potential in the electric field in terms of all the other fields, the low energy fields, okay? So this is sort of reminiscent of spin hydrodynamics in the way that I know. Because you do everything you can do, and at the end of the day, you say, well, the spin chemical potential, spin potential is determined in terms of the other fields, okay? And that's what it was good for. And here is the same. So at the end of the day, I say, the whole theory is determined in terms of dynamics of a temperature and the magnetic field. And if I ever want to know what the electric field is or the chemical potential is, I just use this expression, I plug in this thing, and I have it. But in practice, I could literally remove the chemical potential and the electric field from the description. And that's where higher form symmetries come in, okay? So what is the dual formulation of MHD? There's a big historical record about this that starts already with the idea of higher form hydrodynamics. It's less well known, but the first references that work on higher form hydrodynamics actually come from black hole physics in higher dimensions, okay? But then people realized, not by looking at these papers, but independently, that this can be applied to magnetohydrodynamics. And there's a very long list here of things in chronological order of people who have worked in this. And it goes on. This is a selection. And there's even many more, references if you consider higher form symmetries as a whole, okay? But just for MHD, these are the papers that I am aware of. Okay, so how do you end up with that description? If you have Maxwell's equations, you have Maxwell's equations here, you have the Bianchi identity, you can dualize these equations by literally defining a current, a two-form current, saying that it's the Hodge star of F, okay? So this that I'm writing here is just electromagnetic duality when there's no charges, okay? And you find the dual Maxwell's equations in which the Bianchi became the conservation law of a two-form current, and the Maxwell's equations became the Bianchi for that two-form current, okay? And that has a conserved, global U1 form symmetry, has a conserved magnetic symmetry because of this, okay? So if we look now at the MHD equations, which are these, I just told you that I can literally forget about this equation because this equation just determines the electric fields and the chemical potential in terms of the other fields in the game. So I can literally say, I don't care about it. And then I just look at this equation here and at the Bianchi identity. And I dualize the Bianchi in this way, okay? And I rewrite the external current through this equation. I put back the external current in there. I rewrite the external current in terms of a field strength of a two-form gauge field, okay? So the two-form gauge field is sort of the dual to the two-form current. Yeah. Yes. There's a very non-trivial relation between them, I'll show you. But now it's just at the level of equations. Forget about the exact form of things, okay? Yes. Yes. It contains the electromagnetic part written in a different form. Of course it does. But there's no. But yes. It contains the fields. I mean, it's mhm. Yeah. It's just a big reshuffling of things, but everything is there. Yes. Yes. Yeah. 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 Yes. Yeah. Yes. Yeah. I mean, the confusion could have already come before when I showed you. But okay. Yeah. All right. So one thing I have to tell you is that very unfortunately, in equilibrium, it's not possible to generate a non-zero two-form current unless the one-form symmetry is broken in some way. There's just no way of generating that. This is not specific to higher form fields. It's also found, for instance, in the fracton literature. I think I put the references there, in which instead of a U1 gauge field, you have a gauge field with different indices, and that somehow causes the fact that I cannot generate an invariant in equilibrium unless I break the symmetry. Okay, so let me just give you a very brief idea of how you break the symmetry. In a conventional U1 breaking that I showed you before in a superfluid, I introduce a Goldstone field, which is a scalar field, shifts linearly with the gauge parameter. I define a superfluid velocity that is invariant, and I have a Josephson equation that tells me the evolution of that Goldstone field. In the one-form case, is the same thing. except that now your Goldstone field picks up an extra index, okay? So there's a mu index there that shifts linearly with a two-form gauge parameter, okay? You can define, instead of a one-form superfluid velocity, you define a two-form superfluid velocity that is invariant under that gauge transformation. So this is the two-form gauge field that transforms with the derivative of a one-form gauge parameter. And you also find a one-form Josephson condition of this kind, which is just a generalization of that one. You can see the definitions here of the one-form chemical potential, et cetera, how you make that invariant, okay? Is the external gauge field, yeah, that I dualized here, right? Sorry, which one-form symmetry? The only one I have? Yeah, so I have now, sorry. So I have this symmetry here. This is a one-form symmetry. And I'm spontaneously breaking that one. So the equations don't change in the same way that in the superfluid, it doesn't change. No. Yes. Well, right, I think then we have to have a deep discussion about what equilibrium is. You want to write an equilibrium partition function that describes all the equilibrium states in your theory, not just one particular one, as in the superfluid case. So there we leave the Goldstone arbitrary because we want to describe all equilibrium states. We don't choose the gradient of the Goldstone or the superfluid velocity to be a specific thing. We let arbitrary because there's many equilibrium states in the theory. Okay, but right, yeah. Yes. A la many. A freezing of the phase transformations, something that people never explicitly say. They shift their phases by a spatial part, they froze the temporal part, and they just say, for instance, yes. So you freeze that shift symmetry, and people typically say, well, I froze it because it gives me the right MHD dynamics. Yeah, indeed. If you don't freeze it, no, I mean, you don't get, no, but that's a matter of constructing the invariance and everything. If you don't freeze it, you're in trouble. Like you cannot find invariants that give you a non-zero J mu nu. Okay, so yes. I think so, yes. That's my view on this, and it seems to agree with what Nabil did also in one of his papers, which is in two groups. It's all consistent, and I think there's no shame in it. It's just work. But anyway, I mean, I don't want it to be contested, but let me just say it has a practical utility in equilibrium, and you will see it in a second. It doesn't disagree with anybody. So this is a fully broken phase, which is what I just showed you, okay? And in this fully broken phase, this is an insane theory, okay? All right? So it has actually, you can do a counting, 166 coefficients. This is an insulating phase of electromagnetism in which electric fields and magnetic fields can enter, but there's no free charges in the game, all right? Let me show you in a second. If you assume that the electric fields are negligible or they're first order in this theory, which is just an extra assumption, it doesn't come from symmetry, you can actually get just 11, okay? Now, this thing is the thing that you've never seen before, which is related to what Sajo was saying, which is here I'm talking about sort of a temporal spontaneous symmetry breaking. And what that means is that instead of introducing the full Goldstone field that has an index there, I have to remember that in hydrodynamics at finite temperature, boost symmetry is broken. That means, I have a fluid field there, And because of that, I can break the higher form symmetry in different subgroups. I can introduce just the Goldstone along the flow and not the full Goldstone field. So then I can actually define a scalar, which is basically, you could think of as the contraction of this with the flow velocity that transforms as a shift. And then I define a one-form chemical potential in terms of this thing. And in MHD, I claim this is the partition function. And let me just be explicit about what it gives me. Sorry, I forgot about this slide. This slide, maybe you know, is hydrogen deuterium fluid at high pressures. This is just to give some motivation here. There's a phase diagram that goes from a dielectric fluid to a metallic fluid, okay? I'm not claiming this is the theory that I wrote down that describes this whole thing, but it's very similar. Here, there's no free charges, so you're kind of in this phase over here, and as you increase, thermodynamic parameters, you go to a semiconductor phase in which you start knocking out some more free charges, and then in the metallic phase, you have literally propagating magnetic fields, and the free charges can go wherever they want. So that will be kind of an application of these two phases, all right? So, forget about it, yeah. Okay, now, let's define the partition function for this thing. And it's just given in terms of those two things. I can vary the partition function to get precisely the format of the constitutive relations of MHD at ideal order, okay? And now back to Sasso's question. Because this has implicitly the Goldstone that I defined, the temporal Goldstone, I can vary also this partition function with respect to that Goldstone field, okay? And what do I get? I get this equation here. This is the Gauss constraint, okay? This is interpreted as a Goldstone equation for that Goldstone field. And the Gauss constraint just tells you that there's many magnetic field configurations that an equilibrium solution can have. There's not just one, there's many. And you can open, I don't know, Jackson's book and find many equilibrium configurations for the magnetic field. Yes, the magnetic Gauss constraint, yes. This is the purpose of that Goldstone field, is to say, actually, I don't have a free energy, I have an effective action for a field that describes the degenerate equilibrium states in MHD, okay? Yes. Yes. What is the phi? It's like a magnetic scalar potential. It's a part of that. Yeah. Yes. So the phi here, literally the direction of the magnetic field, so you didn't let me go there, is defined in terms of this combination that evolves the phi. To be able to introduce something that is gauge invariant, I need to introduce that phi to make it gauge invariant, okay? This is how you define it. And then the identification at the end of the day is very simple. So, like I said, this H here, which tells you the direction of where your magnetic field lines are lying, which is defined in terms of that scalar Goldstone field, defines for you the magnetic field in the other traditional language, if you see what I mean. This is how they are related, okay? It's only a constraint equation, so it's, yeah, it's not no, it's not, yeah. So you can play the same game, okay? And you can say, how do I correct this theory? And now I have to correct this theory with playing around with this H field, with the associated chemical potential with that H field, and the temperature and the flow velocity. There's, not surprisingly, 5 different hydrostatic terms you can add to your partition function, which was the same number that I had in the normal traditional formulation. And then I can parameterize both the stress and and the two-form current in the Landau frame. I go on and I find again 19 dissipative coefficients, okay, which was precisely the same number I found before. All right. If I impose on Sager, it reduces to 14. And here, this complicated thing is the map. So some of these coefficients that you see here, 1, 1, etc., are coefficients in the first formulation that I showed you. The other ones are coefficients in this formulation. So, you know, they're related. They're exactly the same in this hydrodynamic framework. Okay. Are they what, sorry? No, the tildes are parity breaking. The cross is cross. Yeah, they mix U and H and U directions. Yeah, I think it was actually, if you want to blame someone, you blame Sasso, I think, for that notation. Sorry. Totally. Yeah, Sasso's result is the black ones without tildes. Pavel's result is black ones with tildes. J's result is everything. So this is just additions on additions on additions and some, you know, breaking, temporal breaking. No, no, the counting has nothing to do with temporal breaking. Temporal breaking is about defining the invariance in a gauge invariant way, defining the general partition function. That is where you need it, okay? And in the common law of modern hydrodynamics, you have to start, in the passive system, you have to start with the partition function because that describes the most general equilibrium states. You know, maybe some people have a different opinion. For me, the partition function is the best thing that has happened in the past, you know, century in hydrodynamics. And I only know how to do hydrodynamics if I can go away from the partition function. If I cannot, you know, I'm going to screw up somewhere at some point in time. But that's my point of view. I'm very strict about the partition function. Yeah. I mean, this doesn't make any difference at the level of counting coefficients. It just tells you, there's also equilibrium, you know, to define hydrodynamics away from global equilibrium, I need to introduce that field. It also says, you know, well, look, there's actually a very general class of states that have to satisfy the magnetic Gauss constraint, and that's the most general equilibrium class of states. And that allows you to sort of describe, for instance, flows that are rotating in which the magnetic field is not aligned with any killing direction, in the magnetic axis is different than the rotation axis. You know, there's just a bunch of configurations out there that are in equilibrium that people like in astrophysics. Okay, so I'm going to discuss causality and stability in these theories. I don't know how much time I have. I have 10 minutes. Yeah, that's totally fine. It's very quick. All right. So in a normal relativistic fluid, neutral, everybody knows, you can think about perturbations around equilibrium in this theory to find the linearized fluctuations in the theory. And as everyone knows, there's a gapped mode that is unstable. This is known for a while. It has been revived recently by also people who are sitting in this room. And besides not being stable, is also acausal. So, right? So this is the problem of relativistic hydrodynamics that everyone knows. Now, how to deal with this? You know, before I came here to this conference, I thought there was just the two first options here, MIS and BDNK. Now there's some people in this room that, you know, kind of convinced me that I should have done something else. But what I've done here was to think about how to introduce, how to do the BDNK sort of fixing of this magnetohydrodynamics theory, okay? And that's what I'm going to focus on. So now I have exactly those equations I wrote down in one form language. I could have done this in the traditional language, but you know, this is simpler, symmetry based. I don't need the electric fields, etc. So I start with this, and I look at fluctuations of this theory by fluctuating both the temperature, the chemical potential, the direction of the magnetic field. And I can write a general parametrization of my stress tensor that now is not in the Landau frame. This is the BDNK sort of procedure. You have to add every single thing that you can add. You don't fix the frame. Fixing the frame, in the special case in which I don't have any, that I don't have parity odd terms, gives me 7 transport coefficients. The general frame gives me 28 transport coefficients. And I wrote there big applause because that's what you should be doing. Because playing around with 28 coefficients is not exactly easy, okay? So if you don't fix the frame, this is the problem. This is in the Alphen channel. You will have a gap mode in the Alphen channel that leads to an instability because this has to be positive. This is a resistivity. Then this is going to be unstable. So yes, I'm sorry. Yes. I'm sorry. Yes, not fixing the frame. This is what happens. 28 transport coefficients, you saw it, you can forget about it. So what I want to do is to study what conditions, what are the conditions that I need with that big system of equations to get a stable and causal evolution at the linear level, okay? So there's a causality constraint, there's a stability constraint, and now you have to use all the methodology that some of the people here developed and others to sort of analyze this system of, I don't know, quartic and quintic and stuff polynomials, okay? And what happens is that there's 2 channels. There's a magnetosonic channel, there's an Alphen channel, there's 13 modes, 7 are gapped, there's many inequalities that you have to sort of deal with. This is an example of inequalities that you get by imposing these constraints on that very general 28 transport coefficients, okay? So this is kind of examples, and then there's a lot of other examples that are very complicated, that they don't fit this page, it's hard to study. All right, and that's the problem, it's hard to study. Ideally, when you do this kind of system, this kind of trick of BDNK, what you would like, really, is to say, if I have an arbitrary equation of state, if I have an arbitrary type of transport that satisfies the second law, does this work? Can I find the BDNK frame? Can I fiddle with these extra coefficients in such a way that it would work for all of them? In this system, I couldn't make that thing, I couldn't solve that, okay, because it's very complicated to analyze. So what I did is that I chose an equation of state and transport properties in a specific case. So I took here the what? Yeah, maybe. You have to do a big scan of parameter space. But so what I did is that I took a paper by Sasso and Napat, in which they had a holographic model of MHD, and they computed in different regimes, at least they have some analytic formulas in the weak field and strong field of all these quantities here, okay? The physical transport coefficients, okay? And I went to the weak field because that was easier. I put that into my conditions, and I started scanning parameter space. I took some, LSD. I had a lot of luck, and then I ended up with these plots. Okay, I found a kind of big region of parameter space in the middle of the swampland, in which the sort of causality is always satisfied for all the modes. Here, the dashed lines are the speed of light, so it's always within the speed of light, and the imaginary part is always negative. And to do that, I had 7 physical transport coefficients, and I had to turn 7 BDNK coefficients to make that causal unstable. Okay, so it works as it should. Okay, for this equation of state. All right. You could try other equations of state and see what happens. I'll show you another equation of state for astrophysics that people like. All right? Yes. Yes. Well, the assumptions is, I mean, these are the assumptions. I mean, I mean, I took the physical transport coefficients. I mean, otherwise there's this, yeah. And that's why, I mean, in the neutral case, you can find a solution for arbitrary equation of state and transport. In the charged case, I think you cannot already with the U1 generically. So that even just with the U1 is already, you know, insane. If you go to the conformal limit, you can do it. If you don't do it, you know, it's already insane. So, you know, totally expected that if I make the system even crazy more complicated, that I won't be able to solve it, okay? All right. So numerical implementation. So I have this astrophysics friend at the University of Amsterdam, and I went to him and I said, you know, I have 28 coefficients, put that into code. Can you guess his answer? That was his answer. It ain't gonna happen. So we had to find a different way of doing that, okay? And in astrophysics, there is, you know, people don't care yet, you know, about viscosities. As far as I know, people just don't care about viscosity, bulk viscosity, you know, all the things that people have looked at. These are ideal MHD things, black hole backgrounds, neutron stars. There's nothing like the quark-gluon plasma happening over there. You know, they didn't even know what the equation of state is. They don't even know what the viscosities are. You know, you cannot do an experiment in the lab to test it. You know, it's reasonable. But they have one theory that they like that implements one dissipative coefficient, okay? And that's called resistive MHD, okay? What do? The only thing they do is that they add a conductivity term over there, okay? Typically isotropic, so that the sigma parallel is the same as the sigma perpendicular. It's called resistive MHD because 1 over the conductivity is the resistivity, okay? Now that transport is obviously dissipative, but the reason why they have always used it for a while without any problem is that it happens to be causal and stable, okay, for the equation of state that they use, which is an ideal gas, okay. So for them, we can put this in the computer. There are codes out there. They can run it. They're very happy with that theory because it happens to have no problems, okay. All right, there's no viscosity here, right? Ideal or the stress, but conductivity. So what we wanted to do is that we wanted to take that whole 28 transport coefficient model and just pick the term that would dualize resistive MHD into higher form language, okay? We also added a one form, a U1 current, which of course makes the system a lot more complicated, but they keep that at ideal order, so there's no problem. So what you do is that you actually only need one BDNK coefficient to make it causal and stable. Okay, only one, which is that tau over there. You have resistivities in your two-form current, which are dualized to conductivities in the traditional way. Typically isotropic, so R parallel, R perp equals R parallel. And you take the ideal gas, because this is what they use to simulate their things. They consider an accretion disk around the black hole, they take an ideal gas, okay? And then for sufficiently large tau, I can make the system causal and stable, all right? Yes. Yes. BDNK. No, that's why they have been using it for a while now. Yes. 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 So the idea here is, you know, of course, like I said, I wanted the 28 coefficients in the code. That is not happening. Can we just show, for now, that this methodology here is the same, or at least as good, as the resistive one? And then we can build on it later, okay? So you probably know this. I don't know. There is this thing called the back science, the black hole accretion code. It's open source. You want to simulate MHD in different things. You can go there, use their code. You have to sort of, to put in their framework, you have to write your equations into this thing called flux conservative form, in which you choose your sort of so-called primitive variables, and then there's a bunch of numeric sort of tricks to recover these primitive variables, et cetera, et cetera. You start asking questions about that, I get out of the room, okay? I cannot do it, I cannot answer. The thing that we did here is actually added as a module to this Bach library, okay? So we write the equations in this form. It's not too difficult, it takes some time. And then what you want to do is to do some numerical tests with different initial conditions and see how these things perform, okay? So this is one of these tests that people typically do, which is the Orszag-Tang vortex that you initialize with the configuration of this kind, okay? Here you have the traditional thing, resistive MHD, and here you have higher form MHD. Resistivity is 0.002. This is the inverse conductivity, 0.002, okay? And you have a specific tau, which was this Billian-K coefficient, okay? Now you initialize this system and you let it run. This is what happens. This is the density, by the way. Okay, did you see any difference? Yes, there's no difference. There's very little difference. So now this is a different, the same kind of thing, the same configuration at different times, t equals 6, t equals 10. But now I also added ideal MHD, one form MHD, resistive MHD. Yes. Yeah. You can run it on a laptop, but I mean, that doesn't mean I know how hard it is. I mean, you can do it in a laptop, yes. Somebody can do it on a laptop, yes, yeah. But not me, okay. Yeah. Oliver can do it on a laptop, yeah. So as you can see here, there's some differences between ideal and one form and resistive, but not between one form and resistive. That's pretty much the same thing. And I'll show you a better... Okay, I'll show you a plot that you can see really the differences. But here there's a very striking difference. Here there's like fragmentation instability, plasmoids get, you know, formed out there. This is ideal MHD, but then once you put the conductivity or the resistivity, these things get smoothened out. Okay, but let me show you a better plot that you can really compare things. So this is a plot of the energy. Don't ask me why, but in astrophysics, you like to split this into electromagnetic contribution, enthalpy contribution, this is a part of the fluid without the charge, and then charge contribution to the stress, okay? And what you have here is these different lines. So this is the enthalpy contribution, this is the free charge contribution, and the electromagnetic contribution. And then dashed lines are resistive MHD, solid lines are higher form MHD, dotted lines are ideal order MHD, okay? If you trace down this quantity over time, what you see is that there is a big difference between resistive and one form compared to ideal, but very little or almost nothing between resistive and higher form, okay? So there's more tests and more quantities you can you can look at and trace, and you know, it's pretty much the same. Okay. They are adaptive, but you could, but honestly, I think I would like to do it, but it was not famous. I mean, it was not accepted as the plasma in the universe. But that's what I said. Why don't we put the holographic thing? And I was like, holography, what? Yeah, so no. All right. I'm already out of time. I did take 6 minutes for the poll, so I'm 6 minutes, I'm in 1 hour time. So forget about this. I'm not going to talk about higher forms and approximate symmetries as the outlook. So higher forms are useful just because even though I didn't show you, I only gave you the MHD case. Once I generalize to approximate symmetries, you know, there's a web of dualities between these things of how you break it or not break it. And that describes all those phases, or most of them that I showed you in the beginning. Okay, and I like that. Now, there's also, I hope, that I did, maybe I didn't say explicitly, there is a practical utility. The implementation of that equation for higher forms in numerics is faster than running the resistive code, okay? And that's because typically when you do resistive MHD, you take large conductivity because that's the assumption of MHD and that's what people expect, okay? But you end up with the so-called stiffness problem. You have to decrease your time step numerically and that's very costly. People developed a package which is called implicit-explicit solver, very numerically expensive. Once you dualize to MHD, resistivity is 1 over conductivity, that becomes a small number. There's no problem in stiffness, okay? So it speeds up the codes, and that's the interesting thing here. And now, of course, once this, you know, people, my collaborator got convinced that this is a good thing, we're now putting viscosity. We're putting viscosity in this thing. We already have it. I don't have anything to show you now. I cannot show you. And we also have different kind of tests, numerical tests that we've performed, okay? There's also something that people call the variability problem in the Event Horizon Telescope, okay? It's just that seems that the accretion, the way they simulate the system with their ideal order MHD or resistive MHD has a lot more, a lot less sort of variability than the data. It's just changing too rapidly, okay? Some people think, it's not all of them, but think that including dissipation by means of viscosity, etc., will make this a better fit, okay? So that's kind of the motivation for, you know, let's use dissipation in MHD, okay? For astrophysics applications, maybe not for the ones that you're interested in here, okay? And then you can really try to understand more in depth the phase transitions between these phases once you include approximate symmetries. I showed you at some point that there was 2 phases, fully broken phase, temporal phase. In the fully broken phase, there's no free charges. If I break that approximately, free electric charges become topological defects of the higher form electric symmetry. As I increase, let's say, somehow increasing, I have some process increasing temperature that somehow increases the density of free charges, I can go from that phase to MHD. So that's a kind of plasma phase transition from a non-conducting phase to a conducting phase by cracking up the topological defects in the electric one-form symmetry, very much analogously to when you melt a crystal by increasing these locations in a spatial symmetry, okay? So there's many things to explore, and that's it. Thank you. Yes. I mean, it just depends. So correlation functions, if you compute it, you know, where you can find, you know, expressions for the transport coefficients, there's only 7. All the others I added are BDNK things. Whether that's observable, you know, I cannot see it with the correlation function, but I don't know. Yeah. Maybe somewhat, you know, this is BDNK discussion, and I'm not, a BDNK flow. I don't know if is this transport coefficient, does it become physical when you take it like that or not? I don't know. Do you have an answer to this, or do you have an opinion? Yes. So there's somehow some relation between those and the others. Yeah, the billion K and the physical ones. Yeah. No, I understand. Yeah, so you're saying the billion K coefficients are determined in terms of the others. Is that what you're saying? Okay, all right. Okay. There's no Kubo formula for it. No. Yeah. Yeah. Okay. You should. Yeah. Okay. 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 That's a different discussion, indeed. Yeah. 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 I don't know if I can say that, but yeah, they're becoming a bit worse at late times. Yeah, that's true. Yeah. Yeah. No. No, I don't know, and I don't know whether that continues to be the case. Yeah. Well, the black, forget about the black line because that's a different observable. That observable. That's the. No, I think he's talking about. I think he's talking about this thing here. So the dashed line here is coming a bit off from the solid line here at later times, while here is a bit more on top of it. Okay. So yeah. So we're performing more tests now to try to understand what happened. So I don't have the full answer about, whether this continues, whether it stops or not. Yeah. Yeah, the black line is a different observable. Yeah. Right. Right. Like over here. Yeah. Yeah, it could be. That makes a bump in the red line. Yes. Yeah. We did some tests about that, and it's a minimal dependence on this. Yeah. After a certain value, so you have to sort of make that guarantee that causality and stability is guaranteed, and once you do that and you increase tau, the sensitivity is very little. It doesn't change much. Yeah, it could be, and I think if you increase tau, for instance, these things become better at this time. But yeah, so there's always something that you're not going to be fully satisfied with this, I think. Yeah. Yeah. Yes. No, it's just because I have the one-form symmetry, I don't have to deal with Maxwell's equations, and that's where the problem comes from. I literally don't have Maxwell's equations. I don't have to solve it. They have this conductivity. Yeah. So, or I bypass it. Yeah. Yeah. I know, I don't know what's the correct answer. Yes, I agree with you. Yes. I don't know what the correct answer is. You have to, you know, compare it with something real. Okay. That what, sorry? The what, sorry? Zuparev, okay. Okay. Right. Is also compatible with, is the same, you say? Okay, I do not know this work. Okay. So when was that paper out? Recently, okay. Then you should know everything that I presented here because this is from 2018, some of it. Okay. Yeah, but here the resistive, just resistive, there's no need for Israel steward because it's causal and stable. I don't know. Yeah, there's no need. If you now put viscosity, then you have, yeah. Exactly. That you cannot do it. Yeah, sure. No, sure, 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 sure. Yeah, yeah. Yeah, but look, I didn't, like I said, if yeah, next time. Yeah, yeah.